Okay, so let's talk about work and energy. Here we have a picture of a pitcher who is applying a force onto the baseball, and this force is going to cause the baseball to experience a displacement. So we would say that the pitcher is performing work onto the ball. So let's talk about what work is. Work is going to be a force multiplied by the distance that the object is moved due to that force. So when we look at this illustration, we have a woman here who is pulling on a rope in order to move this box a horizontal distance. Now, before we begin to analyze her force applied, let's take a moment and let's just look at a very basic illustration of an object that we're going to have on a horizontal surface. So vertically, we have the force due to gravity, the normal force, those would be balanced. So we have vertical equilibrium, but let's focus on the horizontal force here. If the woman is applying a force so that force is parallel to the ground. So if she were to squat down real low and pull so that she's moving in a she's pulling along a perfectly horizontal vector, and that is going to cause the object to experience a displacement, then we would say that the work she performs is all of the force being applied times the distance that the object has been moved. Now the formula here says FD cosine theta. So as we go through the notes, I'll talk to you a little bit more about how that cosine theta plays in to both our concepts and our math work. Initially, we're going to be talking about objects that are moving either in the horizontal or vertical plane. So we're going to stay one-dimensional for the most part here in the beginning. And then later we'll talk about things that are on an incline where we'll be putting in some of those measured angles that we've done with some of the other chapters before. So let's go ahead and look at the vector where she is pulling at a diagonal. Now you should understand that all diagonals can be broken up into both their vertical and their horizontal components. So right now the woman is pulling so that some of this force is actually in the vertical upward direction. Some of that diagonal is in the vertical direction. So let's think about it. If she is pulling up, is that force going to be used in any way in order to move my object some horizontal distance? No, the component of her force that is vertical is not going to be responsible for doing the work that causes this crate to move horizontally. So that means that it's simply the horizontal component of her force, the one that is parallel to the ground, parallel to the direction that the crate is moving, which would be parallel to the ground in this example. So that is going to be the force component that's actually going to be used in order to create the work. So since they tell me here that I know this angle, from this angle, this horizontal force component is the adjacent side of my hypotenuse of my right triangle, and so that's why it ends up being FD cosine theta. Okay, so when we start talking about forces being applied at an angle, we'll have to go back and remember that it's only the force component that is parallel to the direction of the motion. That's the force that's going to be used. So one way you could say the woman is more efficient if she were to pull perfectly horizontally, like our first illustration. The other example here, the other illustration, she is not using all of her force. She's only using the adjacent component or the parallel component in order to do the work. Okay? All right. I also need you to know one very important thing about work, and that's that it is scalar. So just to review, scalar is a category of variables that have magnitude only. Magnitude only. We've talked a lot about vectors where it's magnitude with a direction. Work is scalar, which means that I'm not going to assign right is up or north or left or down is going to be positive and this direction is going to be negative. That's not how it works with work. Work is a scalar vector, or I'm sorry, a scalar quantity, not a vector, which means that we're going to have to interpret how things relate to the motion, not necessarily a set direction, okay? And we'll address that in more detail as we move through the notes. All right, so let's talk about the units for work. If work is equal to force times distance, then we should know that we want our force to be measured in newtons. We want our distance or our displacement to be measured in meters. So this gives us a unit of a Newton meter. Similar to how we said that we are going to have a kilogram meter per second squared, and we're going to refer to that as a Newton. We will say here that a Newton meter will be referred to as a joule, and we're going to write that with a capital J for our unit. You may get some questions where we give you values in Newton meters, so I just want to make sure that everybody is aware that that is the same thing as a joule. Now let's look at the illustration that they've given us here. I have a man and he is carrying a bag of groceries. Now, if you look at this picture, we do have some force vectors here, but I also have a displacement vector. So this means that as the man is holding the bag of groceries, the groceries are also going to experience a displacement where it moves some distance, and according to this illustration, the bag is going to be moving to the right. Now, it says in the reading that as long as the person does not lift or lower the groceries, he is doing no work. So we need to make sure that we understand how come this would be interpreted as no work. So when we look at our formula, we say that it's force times distance or force times displacement, but there's a really important piece of information that we need to address. The force vector and the displacement vector must be parallel in order for there to be work. So let's look at this. He's carrying the bag so that the object experiences a displacement, in this case forward or to the right, according to our picture. Now, what force is the man applying onto the bag? He is responsible for applying this force right here. This is the force that comes from the man. So this force is in the vertical upward direction. The displacement is in the horizontal or to the right direction. Now, because these two vectors are not in the same direction, we would say that he does zero work. It says the force he exerts has no component in the direction of the motion. So our force and our direction of the displacement need to be in the same direction, okay? We've got to be parallel for those two vectors. So this would be an example of no work done. I also wanted to take a moment to address this downward force vector here. Now this is going to represent the force due to gravity, and I just simply want to point out that the Earth is attempting to do work on the bag. The Earth is attempting to apply a force to create a vertical displacement where both of them would be downward. But since the object is not experiencing a downward displacement, then that downward force due to gravity also does 0 joules of work on my object. Now, we were just talking about circles, so let's look at the situation for my moon that is orbiting the Earth. When we look at this moon, we know that it has a tangent velocity vector. This velocity would be tangent to the circle. This represents its path of inertia. So we know because of Newton's first law that my object would like to continue moving with a constant speed in the same direction. But if there is a net force acting on it, it will change either its speed or its direction. So the moon would like to be moving along this vector path. However, it is experiencing a force from the Earth's gravitational pull that is not going to allow it to follow that vector path, but instead it's going to cause it to accelerate towards the Earth. So once again, this becomes a situation where there is no work done on the moon by the Earth. So if I were to ask you, yes or no, is the Earth performing work on the moon? The answer is no. Now you may be thinking, but I don't understand, because the force is responsible for changing the moon's path so that it is turning. It's moving back towards the center of the Earth. And that is a true statement. That is responsible for the acceleration. However, when we're talking about work, we have to understand that it's the relationship between the force vector and the displacement vector. So the velocity vector here shows the direction that the object would move. So this would be the displacement vector as well, or at least it would indicate the direction of the displacement. So if we look at how these two vectors compare to each other, they actually have a 90-degree relationship. So let's look at our formula for work. This says that work is the force times the displacement times the cosine of theta. So listen, conceptually, you can understand that they are not parallel, they're not in the same direction, they're perpendicular to each other, therefore there is no work done. And that would be sufficient for understanding those conceptual questions. However, I want you to understand how the formula relates, okay? So if we understand that the angle between these two vectors is 90 degrees, then we would say that it's force times the displacement times the cosine of 90. And the cosine of 90 degrees turns out to be a value of 0. So even if we felt like we should be plugging in a force times the displacement here, once we indicate that that angle is 90 degrees, once we understand that it's times the cosine of 90, then what we're saying is that we're going to multiply it by 0. So regardless of what information you wanted to input for your force and your distance, this comes out to be 0 joules of work. No work is done, okay? Let's go back up here to our example of the woman pulling on the crate. So right now I want to focus on the example that I made up for you. If she were to apply the force perfectly parallel to the direction of the object's motion. If we were to plug in our numbers here, we would say that it's the force she exerts times the displacement that the crate experiences times the cosine of the angle. Now, if the force and the displacement are parallel, if they're in the same direction, then our angle here would be 0 degrees. And the cosine of 0 is 1. So if we are multiplying times the cosine of 0, we are simply saying times 1. So in general, if the object experiences a force like the illustration that I have drawn for you, then it's essentially at face value the force exerted times the displacement experienced, because once we consider that angle, we're just multiplying by 1. Okay? All right. So what does it mean to have negative work? Because I've shown you on that last example how we could have work where that would come out to be some positive number, whatever that force and that displacement was. It's going to give us a positive number for our work. And then I've shown you how there is no work done. So what is it if I say that we have negative work? Again, remember that work is scalar. So what does it mean to have negative work? Well, here it says that work is done by forces, that oppose the direction of the motion, such as friction, will be negative. So negative work is work that opposes the direction of my object's motion. Okay, so let's look at this illustration of our baseball player. We're going to say that our guy is sliding into second base. So the guy is running, he's applying a force to move himself forward, but then when he slides, he's no longer pressing with his foot against the ground to move him forward. Instead, it's his inertia that's taking him forward. So we have some displacement, and that is indicated here. And then as he slides across the ground, he is experiencing a force in the opposite direction, which we know is a frictional force. So conceptually, I can say that the force, the frictional force acting on him, is in the opposite direction of the object's motion. So this means that I am going to have work done against his motion. So that would make it negative work. If we look at the formula, then we would say that the force applied times the distance times the cosine of theta. So what would my theta be? Well, if the displacement is in this direction and the force is in this direction, then the angle between those two vectors is 180 degrees. And if we were to take the cosine of 180 degrees, that gives us a value of -1. So mathematically, when we understand that opposite pointing vectors in opposite directions, give me a value of a -1, that means whenever I plug in my numbers here, I'm going to end up with some negative value for my work. Work done by forces that oppose the direction of the motion will be negative. Okay? So this is what it means to have negative work opposing the object's motion. All right, so now we're going to just look over some examples to make sure that we understand the difference between positive and negative work, and to understand that understand when we have work or no work done on an object. So first, let's talk about positive and negative work. Here I kind of summarize it for you, and then I've highlighted in blue what's the most important quick summation here. So for work, positive work means that the object is the force is in the same direction as the object's displacement. Negative work means that the force or the work is in the opposite direction of the object's displacement. All right, so with that in mind, a speeding car skidding to a stop. This is going to be an example of negative work because it would be a frictional force that's bringing that car to a stop. It is opposing its motion, and so that's going to give us negative work. A rope raising a bucket from a well is going to be positive work because the force applied upward creates the displacement upward. They are in the same direction. The work is done in the positive direction. Or we could use our formula times the cosine of 0 and we get a +1 that we're multiplying by. So we end up with a positive value for our work. Air acting on a parachute falling to earth. This would be negative work done if I ask you how much work the air does on the object, okay? So if I have an object, it is experiencing a displacement vertically downward because it's falling. Air resistance, lift, we could call it friction, whatever we want to call it, that air is there opposing the falling object, opposing the motion of the fall. So this once again would be 180 degrees, which is going to give me a value of -1, or we could just conceptually understand that the force that they are asking me about is in the opposite direction from the object's displacement, therefore it is negative work. A teacher applies a force to a wall and becomes exhausted. Now, we are assuming that this is a normal human being, so they are applying a force onto the wall, but the wall does not move, right? All right, so if the wall does not move, then we need to understand that this would be an example of no work being done. Why? Because there would be zero displacement, 0 meters for my displacement. A book falls off a table and free falls to the ground. Yes, this would be work. The falling object would have a downward force due to gravity, and that force coming from the earth is responsible for the object experiencing its acceleration. So the downward force due to gravity and the displacement it's also downward. Same direction, the force is causing that displacement, so yes, that would be work. A waiter carries a tray full of meals above his head by one arm straight across the room at a constant speed. So in this case, the vertical position of my tray does not change. So my tray is not experiencing a displacement up or down. Neither of these things are the case. The tray is only experiencing a displacement in the forward direction. The forces applied to my tray would be in the vertical, downward force due to gravity applied by the earth, upward force from the waiter's hand, but those are not parallel to the direction of the displacement, so this would be no work done. If we plugged it into the formula, we'd multiply by a cosine of 90, which would give me a value of 0 joules of work, okay? A rocket accelerates through space. Yes, work would be done. There is a net force acting on that rocket in order to cause the displacement, so there would be work performed on the rocket. All right, so that is what we need to know about work. It's force times displacement, and when appropriate, times the cosine of theta. And we need to understand when there is work, when there's no work, what it means to have positive work, what it means to have negative work, and remember that work is scalar. So now let's talk about energy. Energy is the ability to do work. I have the ability to perform work because of my energy. So here you have some examples of some physical work being done. The woman is lifting, I guess, what is that? I don't know, some sort of mass. I don't know. Here in the second picture, the woman is performing physical work to lift herself up onto the step. And then the last picture, we are performing physical work here. The truck is applying a force to lift this crate. In all of these situations, work is being performed because of the energy available, okay? Doing work uses the energy that was available. So if I have an object that has work applied to it, so let's say this crate right here. This crate is going to have some work applied to it, and that work is going to be performed because of the energy that was available. Now, as we move through the notes, what we're going to learn is that the work performed is responsible for the energy that this crate has now gained because it has been lifted. We can also say, in the event of these first two examples, it's maybe a little bit clearer to understand here. If the woman in the second picture is doing work in order to lift herself up onto this step, then she is going to be using her energy in order to allow her to perform that work. So after she has lifted herself, she has transferred some of that energy in order to execute the work, and so now she has less energy than what she started with. So kind of big picture, that's the overall relationship between the two. So let's get into some specifics. In this chapter, we're going to be talking about mechanical energy specifically. There are lots of different forms of energy, but right now we're focusing on mechanical energy. And mechanical energy consists of two main categories. We have kinetic energy and we have potential energy. Kinetic energy is going to be represented with a capital K, capital E, and our formula for kinetic energy is 1/2 mv squared. So let's focus on kinetic energy to start. Kinetic energy is energy due to motion. So this is an object that is active. It is moving. We have some sort of velocity for that object. So moving objects have kinetic energy. So we're going to write our formula. Ke is equal to 1/2 mv squared, where the m is the mass of the object that is acquiring, losing, gaining, whatever, this energy. V is the velocity, the speed at which it is moving, which is the most influential about how much kinetic energy the object has. Now, you may choose to also write this equation as mv squared over 2. That has exactly the same relationship. Or you may choose to express it as 0.5 mv squared. All three of these are acceptable. However, on your formula list, it's going to be written 1/2 mv squared. So moving objects have a velocity. If an object starts from rest and then goes into motion, then it changed how much kinetic energy it had because its velocity changed. And we'll talk more about why it changes and how it changes later on in the notes. So our potential energy then is going to be indicated with a capital P, capital E. So 2 letters to represent both of these variables. Now, we could kind of put ballpark descriptions on these 2 types of energies, and we could say that kinetic energy is energy of motion or action, or maybe we could say that this is our objects that are physically active, right? They are in motion here. And our potential energy then would be the opposite of that. This would be our stored up energy. So potential energy we are going to discuss in 3 forms. Now, I'm actually going to start with this last circle here. Chemical energy. You talk a lot about chemical energy in chemistry, and it's the idea that we have energy that's stored up inside of those molecular bonds, and if those bonds are broken, then that energy is released. So in a nutshell, that's the idea behind chemical energy. It is a thing, and we will talk about batteries more later on, but for right now, just that is a form of stored up potential energy, okay? Let's focus today on gravitational and elastic potential energy. So we're going to start off with gravitational energy. So this is going to be a capital P, capital E for potential energy, and then we're going to put a subscript of a G. Now, sometimes this is expressed GPE. They just decided to put the G for gravitational in front of the PE instead of as a subscript. They mean exactly the same thing. Please don't get tripped up on that if you see it expressed in the other way in the future. So our gravitational potential energy is going to be calculated by multiplying the mass times the gravity times the height. Now, if we are talking about potential energy in general, then it is stored up energy, but it's going to be dependent upon the situation, okay? We need to identify what is our system, what is our environment surrounding our object, or determining what's important and what's influential in that system or in that situation. So for right now, we're going to focus on this first example, an object at some height above the ground. So I want you to understand that if this is the ground and I have an object up here, we know that there is a force due to gravity here because the Earth is attempting to create a displacement to bring that box down to the ground, which means that it's attempting to perform work by applying a force to create a displacement. That's what is happening, or that's what the Earth is trying to do to our object. So anytime our object is at some height above the ground, if we have some vertical displacement, then that means we have stored up energy that could then be expressed or turned into action energy later if that object falls because of the force applied to it or the work done on it, okay? So our formula here is PE equals mgh for gravitational potential energy. And we're going to take a moment and we're going to look at this illustration over here. We are saying initially that my object is at this first location. So you can see that they called this Y1. When we talked about displacement and we started talking about vertical motion, we said that we could say delta x for horizontal and delta y for vertical. So that's what they're doing here in this illustration. But we're saying that it has some initial position, and just to make this conversation easier, we're going to say that this is our starting point. So we're going to give this a vertical position or height of 0. Whether it's literally on the ground or not, in this case, does not matter. What matters is that we are using this as our starting point. So when we say mass times gravity times height, you will need to interpret from the question what we are using as our quote-unquote ground level, so that you can determine what the potential energy is from there, or how the potential energy has changed because of where it started from, okay? So for right now, we're just going to say, let's assume that Y1, position 1, is on the ground. This is at ground level, so a height of 0. If my object is raised to position 2, we now have some height, and let's just make up a value. Let's say that this is 8 meters above position number 1, okay? Now that my object is at this new location, I can say that my object now has some amount of potential energy. How would I go about calculating that potential energy? Well, potential energy, gravitational potential energy specifically, is mass times gravity times height. So I would simply input the mass of the object times the acceleration due to gravity, so we are inputting a 9.8 here, times that height, that vertical displacement above our starting point, our reference point, or our ground level, okay? Now, it says here, in raising a mass m to height h, the work done by the external force is, and then we give you a relationship. Work is equal to force times displacement, and then it says times the cosine of theta, so I'll come back to that in just a moment. But in general, the force applied created the displacement. Well, let's look at what we have acting on this object. My object is experiencing some sort of applied force here. They called it force exerted. I'm just going to call it an applied force. And so the applied force is in the upward direction, and you can see they've already provided us with a displacement vector here. So the displacement vector is in the upward direction. So that means that we have positive work done on my object, because when I multiply times the cosine of theta, these are parallel to each other. They are in the same direction where I have an angle of 0 degrees. And remember, 0 degrees comes out to be a value of a positive 1. So my work is going to be some positive number here, because this is work done in the same direction as the motion, or the force applied is in the same direction as the motion, and so this would be considered positive work. Now, if I were to try to calculate how much work was done, then I would need to be able to take that force value, and if they didn't tell me what it was, then I would need to calculate that. So how would we go about calculating that? Well, in this particular example, my object must be moved here at a constant velocity, because what we can see from this illustration is that they have drawn my applied force and my gravitational force vectors as equal. So let's talk about when is that scenario true. Anytime we have an object and it is moving in the vertical direction at a constant speed, we're supposed to know a constant speed or velocity means acceleration is 0. Which means that the net force acting on my object is 0. The net force is the sum of your forces. And in this case, my applied force is in the upward positive direction. My gravitational force is in the downward negative direction. And so the popular vote is to express the formula like this. Okay, no problem. The net force is the sum where they are in opposite directions, so we are ultimately subtracting here. Now, if my net force is equal to 0, then this means that FA minus FG, I would have to add my FG to both sides. So essentially, my gravitational force is the same as my applied force. When I go to calculate what my force value is here, they would be equivalent. So this means my FG would be mg. And since my displacement is in the upward vertical direction, don't want to confuse anybody there, my displacement is in the upward vertical direction, then that means this could also be expressed as a height. And so that's why you see here that it says work is equal to mgh. Now this is whenever we are lifting our object. Specifically, when our object is lifted at a constant speed, then our applied force is going to be equal to that gravitational force downward, okay? So just to review, potential energy is mass times gravity times height. If the force applied is in the same direction as the displacement, then my angle is 0, which just simply means that I'm going to be getting some positive number for my work. So work would be positive. Conceptually, I could say that my object is gaining energy, or we have positive work done on it, so it's going to increase the amount of energy that it has. All of these would be appropriate interpretations, okay? I also wanted to make sure that I took time to address to you that this relationship here of a constant speed is the same if we were in the horizontal direction. So if my acceleration in the x direction was 0, then my net force in the x direction would be 0. So that means that whatever my applied force horizontally minus that frictional force is, this, because of the algebra, would ultimately give me my applied force is the same magnitude as my frictional force. Okay, so this right here is if we're talking horizontal motion. And you'll need to be able to make that relationship so that you can work some of the questions you're going to get, okay? Little side note there. All right, so then let's talk about the other type of potential energy. So we said that potential energy could either be gravitational potential energy, or it could be elastic potential energy. So this is going to be a capital P, capital E for potential energy, and then we're going to give it a subscript of EL for elastic. This will be calculated using the formula 1/2 kx squared. And so we'll spend some time talking about what those variables are. So we've already looked at the example where we have an object raised some height above the ground. So now let's look at these two examples. One is of a spring and the other is of an elastic band, or most students, when I ask, say that the word elastic makes them think of a rubber band. So if we are talking about manipulating either an elastic band or a spring, I need you to understand that we can stretch or compress. In the spring's case, we can compress as well, these two things. And so what we're doing is we are applying a force onto my object that is going to cause it to gain potential energy. We're going to have stored up energy. So winding up a spring, I'm reminded of playing pinball where you pull on that lever to squish that spring together so that you have potential energy as long as you hold on to that lever. And then once you let go, that potentially turns into its action energy, right? But compressing that spring is creating elastic potential energy in the spring. Stretching a band, I'm reminded of a slingshot, where you are taking that rubber band and you are stretching it. So what you are doing is you are applying a force, which is exerting work or creating work onto the elastic band or the rubber band, which has now created stored up potential energy waiting to turn into action energy as soon as you let go of that rubber band, right? Okay, so let's talk about in more detail how potential energy can be represented or created inside of a spring. So once again, we're dealing with stored up energy. Here we have a picture of my spring when it is at rest. So this would be my spring in equilibrium. In other words, if we were to just leave the spring alone, let it settle and come to its resting point, here is how the spring would lie. Now in the second picture, we are clearly applying a force onto that spring, which is also creating some sort of displacement. So the force applied is going to essentially perform work onto that spring. And that work is creating energy to be stored up into that spring in the form of elastic potential energy. And then you can see in picture C, when I let go, sure enough, that stored up energy is now transferred into action energy and it launches the ball forward. So this is kind of similar to my pinball machine example, okay? So the force required to compress or stretch a spring is, let me give you this formula. F for force, capital S for spring, is equal to kx, and we will be using the absolute value of that for our calculations. So this means F, capital S subscript, is the spring force. And I want to pause right here and make sure that nobody gets confused moving forward. We have talked about frictional forces, which could either be static friction or kinetic friction. These were capital F for force and then a lowercase s for static and a lowercase k for kinetic. And that's the appropriate subscripts. And you guys have seen Fs and Fk in previous formulas, and those are appropriate notations. However, I realize that an F lowercase s and an F capital S kind of look exactly the same. So I don't want you to get confused moving forward. So here's what I'm going to tell you. If you think back to any questions that I've worked out for you guys, or if you think back to the assignments that you have completed in Canvas where we're dealing with frictional force, I typically just use the F, lowercase f, for friction in general. Verbally, we discuss that it's the static or it's the kinetic, but whenever I'm identifying my forces, I'm pretty general and I say F of F. So I will continue to do that because we will have frictional forces in this chapter as well. So anytime you see F of S in this chapter, that is going to represent a capital S for the spring force. So make sure that you are not confused moving forward. K is a lowercase k, and it represents the spring constant. Now, this is not a subscript. This is a variable all by itself. This is going to be measured in newtons per meter, and this is a way of telling me how tough, how tight, how stiff my spring is. So if you think of the springs that are used for a trampoline, and then think of the springs, I don't know, take your TV remote, open it up where the batteries go, and you'll see that there's a little spring in there that is used to hold those batteries tightly in place. So let's compare that little spring in your battery holder of your TV remote to the spring on a trampoline. those are definitely springs made with two different levels or amounts of stiffness, tightness, however you would like to describe, whatever descriptive word you want to use there. So when we talk about the spring constant, this is a value that indicates for me how tough or how strong my spring is. So the spring constant for your trampoline spring is going to be a really big number because those are very strong, tight, tough springs. The spring constant for those little bitty springs holding your battery inside of your TV remote, that's going to be a very small spring constant value because those are weak springs, okay? So that's essentially what the spring constant represents. Then we have the letter X, and this is going to be our displacement. And once again, we are going to measure that in meters. So our displacement is going to tell us how far from the equilibrium resting position we have either stretched or compressed our spring. I want you to understand that we're taking the absolute value here when we're calculating our force value. I just want you to understand that the value, the magnitude of that force is however tough the spring is times how far I stretch it or how far I compress it. So it says here on this next slide, the force increases as the spring is stretched or compressed. In other words, if I just want to compress my spring a little bit, I need some force in order to do that. But if I want to take that spring and I want to compress it all the way, the more I compress it, the more displacement I give it, the greater the force is needed in order to create that displacement. So when we are talking about how much potential energy is stored up in a spring or an elastic band, we are going to use the formula PE elastic is equal to 1/2 kx squared. PE elastic is equal to 1/2 kx squared. And so this is the formula that's going to tell us how much elastic potential energy a spring has because it is compressed or stretched, and it's also dependent upon the strength of that spring. All right, so this takes us to our last thing that we need to cover. We have something called work energy theorem or the work energy principle, and it is the idea that the net work performed on an object is responsible for the change in energy. So I'm going to come back and I'm going to look at some of the things that we discussed with energy earlier. We said that work can either be positive or negative. We're working with or we're working against, right? If we think about the situation of my baseball player who is sliding, he is losing some of his kinetic energy because that frictional force is doing work opposing his motion that's causing him to slow down. If we look at the example of my object that was lifted here, this object gained potential energy because work was performed on the object in order to raise it to some new vertical position. So the work that was performed physically by this person then transferred their energy into the box so that the box now has stored up potential energy at its new height. If this box were to fall, so we talked about my falling object, yes or no, is there work done? Yes. This parachute falling, right? We have work that is done on my object. So if the object were to fall because the earth performs work on it, then it would, in the case of our gravitational potential energy, once again change how much gravitational potential energy it has. So if this object were to be lowered, then it would have a decrease in the amount of gravitational potential energy because of the work done on it by the earth in order to bring it to a lower height or a lower vertical position. So what I hope you're catching from everything that I'm saying is that work and energy are extremely closely related. In fact, everything that I have described has told you that the work performed is responsible for the change in the energy that the object experiences. Same thing with our spring. It only gained potential energy because the work that was performed on it. So that's what the work energy theorem is telling us. The net work performed on an object is responsible for the change in energy that it experiences. So when we were saying that we have positive work done, if you go back and look at those situations, I bet those objects gained energy because the work was in the same direction as the object's motion, so the work was moving with the object, so it increased that amount of energy that the object had. When it was in the opposite direction, we said that that would be negative work. And if you go back and you look at those examples, we would probably see, that the object lost energy in these cases because the work was acting against the object's motion. So you see the work is responsible for the change in energy. All right? So now what I want to do is I want to take a moment and make sure that you understand how to write these formulas so that you can have the relationships you need to perform your calculations. So we had 3 different types of energy that we discussed, and we're going to go through all 3 of them right now. So first off, let's start off with kinetic energy. So if my object experiences a change in its kinetic energy, it's because there was work done responsible for that change. So remember, change in anything is always going to be final minus initial. So in general, the work performed means I had 2 different kinetic energies. My object either increased or decreased its velocity, which was responsible for increasing or decreasing the kinetic energy. Either way, I have 2 different values for my kinetic energy. The difference between them is because of the work that was done, okay? So my work is equal to 1/2 mv squared because that's the formula for kinetic energy. Now, I would need to know the final velocity in order to calculate the final kinetic energy minus 1/2 mv squared initial velocity. And in this formula, velocity is the only variable that is being squared. Okay, if we come back and look at this previous slide, sure enough, it was talking in detail about gaining and losing kinetic energy. If the network is positive, then kinetic energy increases. Let's think about that. If my kinetic energy increases, then my object probably increased its velocity, which means that when I do my final minus initial, my final velocity would be the bigger number. So that when I do my math work, I end up with a positive number here for my change in kinetic energy, which means a positive number for my work. Oh, that makes sense, right? If the work is negative, then the kinetic energy decreases, which for kinetic energy, that would mean that the velocity of our object decreased. So when I do my KE final minus KE initial, that means that my final velocity would be some number less than my initial velocity. So when I do my math work, I end up with some negative number. Sure enough, it was a negative change in kinetic energy or negative work done. So it decreased its kinetic energy, okay? It all is making sense now, I hope. All right, let's look at potential energy, specifically gravitational potential energy. So work is equal to the change in the gravitational potential energy, which means that I have my initial gravitational potential energy, my final gravitational potential energy minus my initial. And so since this is gravitational energy, it's going to be mass times gravity times height final. minus mass times gravity times height initial. Now, earlier we were talking about a box that moved from the ground to some height above that, and I made up that height to be 8 meters. And so if we were following this format, my initial height would be 0 meters, and my final height would be 8 meters. And so this last part would just kind of end up falling off because it would equal to 0. But please do not get in the habit of assuming that, because what if we're not having our object starting off at ground level? What if we're starting at some position not 0 meters, not the 0 meter mark? So be careful with that and make sure that you understand that you have to actually input those values there for your positions in the vertical direction. All right, so then that leaves us with elastic potential energy as the last relationship to look at. So once again, the work is responsible for the change in potential energy, and change is always final minus initial. But if we're dealing with elastic potential energy, this is going to be 1/2 kx squared, where it's the final displacement of my spring or band, minus 1/2 kx squared, where this is the initial position of my spring or band. And then it would follow in the same trend. We would have a greater final position if it was an increase and a lesser if it was decrease, right? In this formula, it is my displacement that is being squared. And so these are the relationships that you are going to be responsible for creating. On the formula list, this is going to be the equation that you're going to receive, and it will be your job to take this and expand it into whichever of these relationships that you're going to need to execute your math work, okay? And then here I just had it already spelled out for you. Everything is just expressed along a line, and so sometimes this is a little overwhelming. So I wanted to take you through the progression, because that is something we've done several times in this class. But here you have all of the relationships spelled out for you. Okay, so this is what we need to know about energy. Let's just go over some highlights. Energy is the ability to do work. It is also measured in joules, so work and energy are both measured in joules. We have kinetic energy, which is energy of motion. So the speed of my object is going to be the thing that greatly determines how much kinetic energy an object has. We have two types of potential energy that we're going to discuss in this class. Gravitational potential energy, where it's whatever vertical displacement above the ground. Because the Earth is attempting to accelerate it, we are going to be calculating that using MGH, where the position has the biggest impact on how much potential energy an object has. And then we have our elastic potential energy, which is for bands or springs, where the displacement, how much we stretch or compress, is going to have the greatest impact in determining how much potential energy my spring or my band has. So that's kind of an overview of what we needed to understand about energy.